morning, everyone. This is Sachin Fiske from Electrical Engineering Department, SND College of Engineering and Research Center. Today, we are going to start the time domain controller and its design. So, in this chapter, we study the problems of the controller design such that the desired system specifications are achieved. Controller design is performed in the time domain using the root locus technique. This controller design technique in the frequency domain based on complete body diagram and will be presented. In this chapter, we emphasize the controller design in the time domain for the following reason. With the help of MATLAB, very accurate result can be obtained for both the desired transient response parameter and steady state error. While designing a controller in time system stability will can be easily monitored since this root locus technique is producing the information about the location of all the system poles so that one is able to design the control system that have a specified relative degree of stability. And third one is the controller design using the root locus method is simpler than the corresponding one based on body diagram. Next, this root locus controller design technique are equally applicable to both minimum and non-minimum phase system, whereas the corresponding technique based on body diagram are very difficult to use for non-minimum phase system. Before we actually introduce the root locus technique for dynamic controller design in this section, we consider a class of static controllers obtained through the pole placement technique based on a full state feedback, and the main purpose of this controller is to stabilize the closed loop pole, and it can sometimes be used to improve the system transient response. In some cases, it is possible to achieve the desired system performance by changing only the static gain, and it is indicated by capital K. In general, as the K increases, the steady state error decreases, but the maximum percent overshoot increases. However, very often a static controller is not sufficient and one is faced with the problems of designing the dynamic controllers. In this section, we present the common controllers used in linear system control design. Two main classes of these controllers are discussed, that is PI and phase lag controller, which improve the steady state error, and PD proportional derivative and phase leak controller that improves the system transient response. This combination of these controllers which simultaneously improve both the system transient response and steady state error are also considered here. A simple class of dynamic feedback controller can be obtained by feeding back the derivative of the output variables. These controllers are known as the rate feedback controller and are presented in this section. It is shown that the rate feedback control increases the damping ratio of a second order system while keeping the natural frequency unchanged, and so that both the response maximum present the overshoot and setting time which is reduced. Actually, this controller design in time domain is studied in the previous section, but the design algorithm which produces are outlined for several types of the controller introduced in the section above. The impact of a particular controller on transient response parameters and steady-state error is examined here. Several controller design case studied involving the real physical systems are the several controller design in case of involving the real physical systems are presented, and at the end a MATLAB laboratory experiment is formulated in which the students are exposed to the problems of controller design for real physical control system. So main objective of this are, let us see one by one. Basically, this chapter presents the systematic procedure for time domain controller design techniques based on root locus method. Now the student will learn how to design the different types of controllers such that the closed loop control system will have the desired steady state error and transient response parameter. In addition, the eigenvalue placement technique, which for the control system allows the location of the system eigenvalue in any desired position in the complex plane, is fully explained for the case of single input, single output system. Now we are moving towards state feedback and pole placement technique. So let us consider a linear dynamic system in the state space form, that is x is equals to ax plus bu, where a and b are the constant term, and y is equals to c of x. Basically, in some cases, one is able to achieve the goal, for example, stabilizing of the system, which improves its transient response, and by using the full state feedback, which represents a linear combination of the state variable, that is u is equals to minus f of x, so that the closed loop system given by x is equals to a minus bf into x is shown on the screen. Therefore, this y is equals to c of x and has a desired specification. The main role of the state feedback control is to stabilize a given system so that all the closed loop eigenvalues are placed in the left half of the complex plane. The following theorem gives the condition under which possible to place the system poles in the desired location. This is very, now we are moving towards one theorem. Let us assume that the one pair, that is A and B, is controllable pair, and there exists a feedback matrix F such that the closed loop system eigenvalue can be placed in arbitrary location. Now see here, this is very important theorem, and it will be proved or justified simply for a single input, single output system. For the general treatment of the pole placement problem for multi-input, multi-output system, which is much more complicated, and the reader is referred. So, if the pair A and B is controllable, the original system can be transformed into the phase variable canonical form. That is, it exists a non-singular transformation. Let us consider one matrix which is Z is equals to, likewise in the first row 0, 1, 0 and so on. Then 0, 0, 1, then 0, 0, 0, then 1. Means here if you see the element 1 or the constant 1 is increasing diagonally. Means if we see the bottom line or bottom row here, the value of this 0 can be increased likewise. A0, then A1, A2 means 1 is going to shift diagonally by making the value of first to n term equals to 0. Okay, into z plus all these are the 0, 0, 0 and 1 into u. So x is equals to q into z. By closing a feedback, let's wait, closing a feedback loop with u of z as given in the previous equation. We get one equation that is, see this matrix z is equals to 0 1 0 0 then 0 0 1 0. I'm again repeating, but if we see this last line here, a0 plus f1, then second column it is a1 plus f2, then third column a2 plus f3. As the value of a goes on increases, at the same time the value of f also start to increases into complete matrix multiplied by z. Okay, if this desired closed loop eigenvalue are specified by lambda 1 to the power d plus lambda 2 to the power d plus lambda 3 to the power d, so that lambda n to the power d, then the desired characteristics polynomial will be given by delta d of lambda is equals to lambda minus lambda 1 d, lambda minus lambda 2 d and lambda minus lambda n d, that is equals to s to the power n plus a n to the power d minus 1 into s to the power n minus 1. This one is the first term. Now we have to make or subtract the suffix order. Okay, so consider lambda n minus 2, sorry, a to the power d having suffix n minus 2. Now it goes on minus 2 minus 3 minus 4, so that at last we obtain one value, that is a to the power lambda, sorry, a to the power d to the base 0, as we are going to decrease the value n minus 1 n minus 2 so on. Since the last row in the above equation contains the coefficient of the characteristics polynomial of the original system, and after this feedback is applied, it follows from this equation, and so that the required feedback gain must satisfy. The pole placement procedure using state feedback for a system which is already in phase variable canonical form is demonstrated in this example. Then we are moving towards the common dynamic controller. Let us see the diagram given below is for a dynamic controller. So several common dynamic controller appears very often in practice, and they are known as PD, that is proportional derivative, proportional integral, and a combination of this proportional integral and derivative. Also phase lag, phase lead, and phase lead lag or lag lead controllers. So in this section, we introduce their structure and indicates their main properties. In the follows of section, procedures for designing these controllers by using a root locus technique such that the given system will have the desired specifications are presented. In the most cases, these controllers are placed in the forward path at the front of the plant. Our system are presented in this figure. Here see first one by one. A PD controller is given. So this PD stands for proportional derivative controller. All you know about this. And the output signal of this controller is equal to the sum of two signals. The signal obtained by multiplying the input signal by a constant gain Kp and the signal obtained by differentiating and multiplying the input signal by Kd, that is the transfer function, and basically it is given by K of S is equals to Kp plus Kd. This controller is used to improve the system transient response. The second one is PI controller. Similarly to the PD controller, the PI controller produces as its output a weighted sum of the input signal and its integral. Its transfer function is G of S is equals to K plus K into 1 by S to Kp of S plus K upon S. In practical applications, the PI controller is 0 is placed very close to the pole located at the origin so that the angular contribution of this dipole to the root locus is almost 0. A PI controller is used to improve the system response steady state error since it increases the control system type by mover. Now we are moving towards last controller, that is PID. The PID controller is the combination of this PD and PI controller, and hence the transfer function is given by Kp plus Kd, or G of S is equal to Kp plus Kd plus Ks into 1 by S, and here in multiply terms are Ki plus Kp plus Kd upon S. This PID controller can be used to improve both the system transient response and steady state response. This controller is very popular for industrial applications. Now, what is phase lag and lead controller? This phase lead controller is designed such that its phase contribution to the feedback loop is positive, and it is represented where, see this diagram. In this diagram, theta Z2 and theta P2 are given and is shown in figure A and B. This controller introduces a positive phase shift in open loop or phase lead. It is used to improve the system response transient behavior. So in case of this phase lag lead converter, the phase lag lead is obtained as a combination of this phase lead and phase lag controller. Its transfer function is given, that is G of S is equal to S plus Z1 into S plus Z2 in numerator and S plus P1 into S plus P2 in denominator, where this P2 is greater than Z2 is greater than Z1 is greater than P1 is greater than 0. Means all these values Z2, Z1 and P1 will be lie in between P2 and 0. And therefore this Z1, Z2 is equals to P1, P2. It has a feature of both phase lag and phase lead controller. That is, it can be used to improve simultaneously both the system transient response and steady state error. However, it is harder to design the phase lag lead controller and than either the phase lag or phase lead controller. All should note that all the controllers presented in this chapter can be realized by using active network composed of the operational amplifier. Now, what is the rate feedback control? We have to discuss this point. The controllers considered in this section have a simple form, and in most of the cases they are placed in the forward loop in the front of the system to be controlled. Another simple controller that is always used in the feedback loop is known as the rate feedback controller. The rate feedback controller is obtained by feeding back to the derivative of the output of the second order system, or basically it is a system which can be approximated by a second order. That is a system with dominant complex conjugate poles. According to the block diagram, the rate feedback control helps to increase the system damping, and this follows from the fact that a closed loop transfer function for particular configuration. Compared with this closed loop transfer function of the second order system without control, we see the damping factor is now increased to 1 by 2 of the value of Kp minus Kd. Since this natural frequency is unchanged, this controller decreases the response setting time as the system response maximum percent overshoot is also decreased. Sometimes one is able to improve the control system specification by changing the static gain K only. It can be observed that as K increases, the steady state error decreases, but the maximum percent overshoot increases. However, by using a large value for K may damage the system stability. Even more, in most cases, the desired operating point for the system dominant poles which satisfies this transient response requirement do not lie on the original root locus. Thus, in order to solve the transient response and steady state error improvement problem, one has to design the dynamic controller considered in this section and put them in series with the plant or the system to be controlled. In the following, we present the dynamic controller design technique in three categories: improvement of the steady state error, that is PI and phase lag controller; improvement of the system transient response, that is PD and phase lead controller; and improvement of both the steady state error and transient response, that is PID and phase lag lead controller. We should note that these transient response specifications are obtained under the assumption that a given system has a pair of dominant complex conjugate closed loop poles, and hence this assumption has to be checked after a controller is added to the system. This can be easily done by using the root locus technique. So how this improvement of the steady state error can be done? So as in the previous chapter, the steady state error can be improved by increasing the type of the feedback control system, and in other words, by adding pole at the origin to the open loop system or transfer function. This is the simplest way to achieve this goal, which is to be added in the series with the system. A PI controller are defined to get G of S into Gc of S into G of S is equals to Kp of S plus Ki upon S into G of S. Since this controller also introduces a zero at Kp by Kz by Kp, and the zero should be placed as close as possible to the poles. In that case, the pole at P is equals to 0 and 0 at Z is approximately equals to P, acts as a dipole. And so their mutual contributions to the root locus is almost negligible, since the root locus is practically unchanged and the system transient response remains the same, and the effect due to this PI controller is to increase the type of a control system by one, which produces to improve the steady state error. The effect of a dipole on a particular response is studied in the next. Thank you.